Hello students, in this lecture we will be discussing about the piezoelectric coefficient D. Now we all know that the piezoelectricity, it arises due to the fact that whenever we are applying some sort of stress, there is a change in the the charge distribution in the material. Charge distribution, it changes, and that rises to displacement current, formation of dipoles. And by charge displacement change, we mean that suppose there are positive charges and negative charges arranged in such a fashion that the centroid is coinciding, so it is electrically neutral. So an application of stress, it makes the centroid or the positive and the negative charges different, so that rises to an electrical dipole, D plus and D minus charge distribution. So centroid of positive and negative charges in the dielectric, it changes, it not coincident. So this rises to distribution, polarization of the charge, localized polarization, and which ultimately gives rises to the displacement current. Now the question is, this is what we known as piezoelectricity. Now this is actually a coupling of the mechanical effect. There is a stress causing some sort of strain, and also the stress causing some sort of displacement. Again, an application of temperature might also lead to a distribution of similar distribution of charges, which might lead to form, again give rise to D. So this is known as pyroelectricity. I will take this up in our subsequent lectures. Now in this lecture we will specifically focus on the fact that how can we define this piezoelectric coefficient D. Now as we all know that stress is a tensor quantity, so I can write it as Ij. Now this stress, so let's represent this by square brackets, which is a tensor. This is a tensor of order 2 plus ing at present. Now this one gets multiplied by parameter or an called S, which is compliance. In fact, it is 1 by E, the elastic modulus. So we get the strain. Now strain is again a tensor. So we represent the strain as KL. Right. Now this compliance, it can be expressed, will be expressed again by Sijkl, and in terms of matrix you can write it as S11, S12, S13, S21, S22, S23, S31, S32, S33. Now, apart from that, this actually is for this ij part. Apart from that, we'll have more components, specifically along the diagonals. So it will be S44, S55, and S66. Other values will be equal to 0. Similar for this case. This is what the compliance matrix looks like. Sijkl. Now, the reason that it has been written in this form, because if we apply an electric field in this case, now that means if you are dealing with a coupled reaction, that is electric field is also applicable. So electric field will be, since it is a vector quantity, now electric field and displacement are again vector quantities, so it will be represented in terms of column matrix. There are only 3 components. So this one, it shows the vector electric field. Okay, along the diagonals. That means due to this scale, now again if you write the expression only for the stress and the strain expression, it will be something like this, that is E I J is equal to S sigma KL, and this is I J K L. Now, as per Einstein's sign convention, if a parameter is repeated, so it implies that there is a summation over that. So it means that there is a summation over K and there is a summation over L. Now, this again is at a fixed electric field. Now, if electric field is changed, electric field E varies, as so it will cause a change in the stress sigma K L, but since electric field is a vector quantity, so the change in the stress will be in only one direction. Okay, the direction in which this electric field is being applied. Okay, so that is why in the matrix which has been represented by S, we have the usual, apart from this usual Sij, which stands for that, we are only considering on the diagonal elements, which is due to the change in the electric field. Now what about the piezoelectric coefficient? So if we would like to represent the piezoelectric coefficient or represent the coupled reactions taking place, coupled effect, then you need to also consider the piezoelectric part. So in that case, the equation will change to Eij. This will the strain caused into Sijkl into the stress applied plus D into your E. The strain caused by electric field, and now since we're representing it by dt, this is the transpose of it, so we are assuming that in this case the strain is causing some sort of or the electric field may cause some strain. Okay, so when there is a stress which is causing electric field, it is the piezoelectric effect, and if it is the opposite one, if this stress is leading to some sort of strain, we will call it the inverse piezoelectric effect. So the piezoelectric coefficient in this case will be dt. T is the transpose, whereas in this case it will be simply d. So for the first equation that is being represented here, we are representing the piezoelectric part by the transpose matrix d. Okay. Now here another interesting thing is that this is tensor of rank of order 2, whereas electric field is a tensor of order 1. So Eij, when it gets represented in terms of electric field dt, its electric field is in the L direction. So we will now represent this dt by 3 indices I, j and k. Sorry, this is k. Alright. So it indicates that the matrix will have number of components as per ijk. So in Sijk KL we were having 1, 2, 3, then 1, 2, 3, 1, 2, 3, nine, 27 components. But here in fact, instead of having 27 components, we will have D31, D32, D33, the and D44, D55, D66. Let it more clearly. Now, before going to that, writing the terms, as it has been told earlier, the piezoelectric effect, when the stress is getting applied, it is applying in only one direction, and the electron actually flows in one direction, electric field. Although this will have this effect of the stress will have shear components to it, the electric field will be in only one direction. So piezoelectric coefficient one component, let's say the 3, it actually means that the strain, the electrodes, last term represent the electrodes, they are perpendicular to the 3 axis. We consider 1, 2 and 3 axis. It is the last one represent the electrodes are perpendicular to the 3 axis. This represents the applied stress which has been applied and which has caused a piezoelectric induced strain in this direction. In the S direction, the strain is in the S direction, and this D, this is nothing but the strain divided by the applied electric field. So that is why when we are representing the piezoelectric coefficient, let's say D, or we'll first write dt is valid in this case, so it will have only the following components. We have D31, D32 and D33, so and other components will be 0. So this one, it means that this is the same the applied stress by strain. The only thing with the D31 and D33 is the electrodes in this case are perpendicular to the 1 axis, whereas in this case it is the electrodes are perpendicular to the 3 axis. And then we will have D44 and D45. D55 and D66, and if you write, so the equation now, the equation in terms of the strain can be written as D13 is equal to S I J K L sigma KL. This is the first part, where we are assuming that no electric field has been applied, plus the one where electric field is applied is getting represented by the inverse piezoelectric coefficient into E. Now if we write the same thing in the opposite way, that means we are assuming that some sort of electric displacement has taken place, and it is due to the piezoelectric effect D into E plus the compliance into the strain. Okay. So it will be the electric field D, which is equal to the piezoelectric coefficient into the stress that has been applied, plus the strain due to the electric field. Now here we are dealing with the positive or the direct piezoelectric effect. So this D here gets represented as this to be represented as in the following way. So D31, D32 and D33 are here. Then again we have D34, sorry, D44, D55 and D66, and all other terms are 0. This is getting multiplied by the stress. Now, interestingly, the stress here will be represented as sigma 1, sigma 2, sigma 3 up to sigma 6. This is the stress. Now, sigma 1, sigma 2, and sigma 3, it's quite known. The sigma 5, sigma 6, and sigma 4, 5, and 6, they are basically the stress due to these, the extra terms introduced into the matrix, D matrix. So if 4, 4 corresponds to D4, 4 corresponds to a stress of sigma 4. D5, 5 corresponds to a stress of sigma 5, and D6, 6 corresponds to a stress of sigma 6. So this equation, it will be plus the Eij into T at constant, Eij sigma at constant stress multiplied by the electric field E1, E2 and E3. So let's write the equations once more. So the first equation is Eij, and the second equation is Dij, displacement current. So this is equal to compliance something into KL plus something due to the electric field E. This is again equal to something into sigma plus electric field. This is your compliance, which is being represented as IJKL. This is your inverse piezoelectric coefficient. This is again the direct piezoelectric coefficient, and this one is again Eij, strain at constant stress. So this is for the direct piezoelectric effect. Equation stands for inverse piezoelectric effect, and this is for the direct piezoelectric effect.